Well, hello friends. Welcome back to OS Hacking. Today we're going to work on some memory stuff, and I would like to show you what we're going to be doing. So if we open System Monitor here, and let's look at the memory map of some program. So here's the System Monitor itself. We can see that it has a bunch of these memory regions here that are malloc memory. And the way malloc works in the system is that, say that you malloc something that's around 64 bytes large, then instead of giving you a whole page of memory from the kernel, which would be 4 kilobytes, we allocate a whole page and then chop it up into little 64-byte chunks. And then we give you one of those chunks. And then if you allocate 64 bytes again, then we take another chunk out of that block and give you. And when you return these chunks by calling free, then they end up in the chunked block here once again. So basically, this here has a whole bunch of allocation slots in it. And when a chunk block becomes completely free, so that all of the chunks in it are available, then we don't give it back to the kernel right away. Instead, we keep it around so that next time you malloc that size, then we already have a chunk block on hand, so we don't have to ask the kernel for more memory, which might be kind of slow. But in those situations where we're just keeping the memory on hand, I was thinking that it would make sense to mark these pages as not read, not write. So like make them completely inaccessible, so that if you try to do anything with them, it would give you a segmentation fault, and that would help us catch some use after free bugs. But I'm kind of curious. First thing is I want to find out if we tend to have blocks in this state at all. And then I was also thinking about what would be a good way to sort of encourage the creation of blocks in this state. Because I guess one thing is that when you're choosing which block to allocate from, it would be much better to choose a block that's not completely empty, but instead prefer blocks that have something allocated in them already. But I don't know, it's hard to decide which one is better, because then there's the disadvantage of that is that if you keep allocating from something that already has something in it, then you might make it so that that thing never actually gets deallocated completely, leading to larger memory footprint in general. But this whole thing is kind of a balancing act. But right now, we're just going to try to work out. First thing is, do we have any blocks in this state at all? So to figure that out, we're going to go in malloc, and we are going to give names to these blocks, I guess, because right now the names are just like chunk block and then the size of it. But actually, I'll show you this thing as well. So up here we have this constant that's called number of chunked blocks to keep around per size class. And this number here, 32, that's how many chunk blocks we'll keep around in memory, even though they are completely empty. So we'll be holding on to up to 32 4 kilobyte pages per size class. And then these are all of our size classes here. So it would be kind of nice to map these not read, not write, because then you could even imagine in the future that the kernel could be smart enough to yank away the physical page that's backing those allocations and then just use a new one in the future. But that would need a little bit more smarts, because the kernel would need to know that it's safe to do that. But anyway, right now we're just going to look at where this is used. So that's down here in free. So this is free, where we see that after we, let's see, wait, what's this? This block has no used chunks anymore. That means that if the allocator's block count, so the allocator is per size class, if his block count is less than the number of blocks to keep around, then we will keep it around. Otherwise, we'll fall through here and go down here where we actually deallocate the block. So this part here, we're not going to do anything about that. I think once you have 32 empty blocks just sitting around for a size class. We're not gonna keep more around. But when we do keep one around, let's set a name on it. So we have a handy thing for that, which is called set mmap name. We can just call block size, and we can call this empty kept around. Empty and kept around. Why am I writing it this way? Empty and kept around for a rainy day. Maybe we'll call these rainy day blocks. It's kind of a cute name. Rainy day, rainy day, rainy day. Ah, that's cuter. Okay, so then when we actually take one of these rainy day blocks and kept for a rainy day. And then when we actually make use of one of these, then we have to make sure that we update the name so it doesn't still say kept for a rainy day. And I guess that would be in malloc, which is here. So we look for a block. This is how we find a chunk block. So we block all of the usable blocks in the allocator list. So wait, hold on, let's look at the allocator. Forget what this looks like. The allocator is a linked list of usable blocks and a linked list of full blocks. So we're only interested in the usable blocks, because that means that it's not completely occupied already. So then what we want to do is, I guess here, if a block has any free chunks, then this block is selected, and then we come down here. And then if there was no block selected, then we allocate a new block and give it that name here. So I guess here we're just going to say if a block was selected and the block is completely empty, so I guess if used chunks is 0, then set mmap name block size. I'll call it reused. Reused. Okay, so when a block is reused, it will have this name, and while it's waiting to be used, it will have the name kept for a rainy day. Okay. And then what we want to do is when we put the blocks into that state where they're kept for a rainy day, we want to take away the read and write access to it to make it crash if you try to use that memory, because this basically gives us a kind of a cheap it's like a cheap memory protection mechanism, I guess, so that if you free something and you're lucky enough that malloc actually had nothing else left in that block, then it will be marked this way and provoke a bug if you access it. So it's a little bit of a protection against use after freeze, and it just seems like a sane thing to be doing. So let's just take a look at it. So let's see, system monitor, memory map. Okay, so I see at least one kept for a rainy day down there. Got this guy right here, this guy right here. Got some reused ones. And we have some kept for a rainy day guys. And keeps updating as it reuses those blocks. That's kind of cool. So this definitely seems like there's an opportunity here for some hardening. So let's make it so that kept for a rainy day loses these bits. So these names, by the way, they're just temporary, just to be clear. I don't know what we're going to call them eventually. These are just cute names that we're working with, okay? So what we want to do when we're setting this state, we really want to call like madvise or mprotect, I guess. and protect. So and protect block and size. Let's do that after. Prot none. Okay, let's try that. And let's see what actually happens when we do this. So I'm protect. What we actually end up doing is we just do set writable. Okay, so we don't care about the readable flag, it seems like. Do we even have a readable flag, I wonder? Set readable. Okay, if we don't have that, okay, this is going to take a little bit of work. But we can see at least if the writable flag works. So I have to rebuild everything because everything uses malloc, right? I was just talking about dynamic libraries earlier today. Seems like every day I feel a little bit more like maybe it's time to start thinking about that, but not quite yet. Okay, so how did we just screw up? Oh, right. we never give the permissions back. So we gotta do prot read, prot write again. I'm guessing that's what we do up here. Yeah, right. So these are the same protections that we would normally allocate with. Fairly sane settings, I would say. We don't have an exec bit because we are on x86 only at the moment. But some point in the future, we're going to do a AMD 64 port, I think, and then we'll add the executable bit. Okay, what am I screwing up? How am I messing this up? Write to address here. 14CD014. That's here. We're reused. But why doesn't it care about the prot write? Did the rebuild not take? Or wait, hold on. If it's reused, then it should clearly have the prot write thing. Maybe this is not working. Let's see. I guess we should check the bit. I mean, the return value of mprotect. So that's rc. If rc0 cert not reached. And what does my phone want? He says buzz, buzz, buzz. That's okay. Where is mprotect? I don't see it. Okay, so I'm not. How am I messing this up? I don't get it. Prot none. What happens when you do prot none? It just becomes not writable. Is it that we're doing a use after free and we're just already catching a bug with this? Could it be that silly? Well, no, it shouldn't. No, because then it would have it would be writable here because it says reused, so it should be writable. I guess we'll just log what's going on. So sys mprotect pattern Okay. Okay, sys and protect. 14cd0, 14cd0. So we're definitely getting the call here that sets the prot write, because prot write is, I guess, 2. Yeah. So prot write, prot read comes in. Is it failing one of these guys, or? We'll just do this. I'm very suspicious of what's happening here. In perm. Okay, setting prot. So it's setting the prot, but it doesn't take. Why does it not take? Set writable. Wait a minute. Wait a minute. What the frick? This doesn't seem right. Wow, that's a hilarious bug. What the actual hell? Set writable false. That totally works, but there's no way to get it back. Alright, well, that's cool. So the bug was definitely that we were setting the read bit instead of the write bit when you update the write permission. So there's a nice fix just by itself. And of course we have to rebuild the whole freaking kernel because we're changing the VM region definition. Let's just test with this. We should probably boot up at this point. Oh, no, we are crashing a lot still. But are these more reasonable crashes, I wonder? Setting prot 155. Kept for a rainy day. And then are we crashing in malloc itself? Oh, well, maybe I'm being a little bit too fast on setting that bit. How does that work again? These blocks, they link to each other. So to traverse the list of blocks, you have to be able to read each block. Well, that sort of prevents this whole thing from working. So we're going to have to switch this over to using a different data structure. We can't use inline linked lists, because this means that the blocks are kept on a list that they themselves manage. So the block itself contains the next and previous pointer. But this is screwing us over now because that means that we can't free a block, because the block will be accessed when traversing this. So I think we'll use doubly linked list instead. Doubly linked list, and then we can get rid of the next and free pointers up here in chunk block. And probably this will break a bunch of stuff. Head is a private member of doubly linked list. Well, what's it called here then? First? From incompatible type. Doubly linked list. Okay, so how does this thing work? I guess we just want these to be pointers now. All right. I don't know why it's called first in one and head in the other. Block. Wait, what's going on here? Remove. We can't call remove. Remove takes an iterator. Freaking doubly linked list. Why are you this way? You should be allowed to remove an arbitrary. Oh, right. Yeah, but that's annoying. I just have a pointer to the thing. I don't have the iterator. So we're going to need an iterator. So I have to redo this a little bit here, but it's going to be okay. Usable blocks, prepend. That doesn't have prepend. I thought doubly linked list had prepend. We have append. I think we're just going to add prepend. Prepend. Okay, well, we are finding many interesting things. Let's do that kernel change here separately, by the way. Oops. Kernel. Fix and protect. Prot. Right. What was the thing that was not working? Setting prot right with mprotect. Mprotect should fix bug where mprotect would ignore prot right. Region typo in region set writable caused us to update the readable flag rather than the writable flag when setting. I'm trying to flag. Yeah. Okay. That's a good fix. And process CPP. I think we don't particularly need this debug logging, but we can just leave it in for now. Here we're going to need some prepend. We don't have prepend node, so we're going to add that. I'm guessing it's going to look similar to append node. So prepend node. And suddenly I'm in data structure land, and if there is no head, then it just becomes the new head and tail. Otherwise, we assert that there is indeed a head. I mean, we already knew that. We can assert that there's a tail still, that's fine. So we'll do mhead. Prev is node. Node next is mhead. Mhead is node. Boom, boom, boom. And X, we should assert that that node prev is null putter, right? Or can do an exclamation. And here, I guess we could also assert that node.next is null putter. That just seems kind of sane, but at the same time, well, no, let's do that. I think it's okay to have more assertions. More assertions is better than, like, too many assertions is way better than too few. Generally speaking, I think. Now we have to fix a bunch of stuff. So tail is a private member of this. Do we have last? Okay. So we want an iterator here when we're freeing. In order to remove something from this list, we now need an iterator. Yeah, so that's one of the convenient parts about an inline linked list is that in an inline linked list, the element is the iterator. So you can just remove it. If you have an element pointer, you can just remove it. But here, the list just contains pointers. So it's a little bit more involved. So in order to remove it from the list, we have to find it. So I think we can do that here. Full blocks, find block. And why don't you like that? Find, wait, is that a const? This iterator. If I remove, I need an, oh shit, I need an iterator amp. Why do I need an iterator amp to remove? What is an iterator? It's just an iterator is a doubly linked list iterator, which just has a list node inside it. Right. So that would be fine for remove to take a value instead of reference. Makes no difference to me. And then we can do things like that. So it's a little bit sad that we have to actually scan the list to find the block to be able to remove it. But maybe that's okay. Okay, allocator for blocks, find block. Find block. I feel like, did I make a typo here somewhere? Usable full. Let's just do a rebuild. Oh shit, where did I screw this up? Inline linked. Oh, I'm inheriting from inline linked lists, so don't need to do that. Don't need that file at all, in fact. And struct chunk block has no next. Yeah, that makes sense. So we want to iterate over this thing, done. I guess we should structure this differently now. So auto candidate block and allocator usable blocks. If candidate block has free chunks, then block is candidate block. Boom. Oh, and we're screwing up here as well. All right, so that switches us over from an inline linked list, or an intrusive linked list, if you will, over to the doubly linked list. Or actually, no, it switches us from inline linked list to doubly linked list, because intrusive linked list is another class. But we can't be using those. Okay, can we boot, please? Okay, computer, what are you doing, dude? There's OBS stuff. All right. And here we are very dead. Get stuck allocating. Okay, well, I guess we did something very dumb now. So what might that have been? Did I just totally crazyfy this thing? I don't think so. Mhead prev is node. Node next is mhead, and then mhead becomes node. I think that sounds good. Okay, so then, did I screw up the malloc changes maybe? So we look through all the usable blocks. If you find one with free chunks, then we choose that one. Okay. And down here, I guess we could keep the iterator from here actually. So we can do something like equal type allocator usable blocks begin block iterator. No? Okay, we'll just do it this way then. Allocator usable blocks begin. All right. And then block iterator is not allocator usable blocks end plus block iterator. We're just going to do it this way then. This is going to be better anyway. Block is going to be block iterator. Awesome. Let's see. In this case here, the block iterator is not valid after this point. Oh shit, right. So, wait, I didn't solve anything by doing this. I just made the code look worse. Because I was thinking I could keep the block iterator around and then remove that later, but in the case here, then, I mean, actually, hold on. I was thinking in the case here where we don't find a block and we have to add one, we could actually just use the block iterator, create a new block iterator here, because we append, so it goes right at the end, and we could just say block iterator is allocator usable blocks. Wait, what does end point to? Is that just null? Yeah. Oh, that's so annoying. We can't get that to the end easily here. Okay. Take it all back. We can probably come up with some better data structure for this eventually, but right now I just want to move forward with my feature. Okay, so what's the dumb typo that I made that's screwing all of this up? It's right here, isn't it? Usable blocks remove, full blocks find. That doesn't sound right at all. Removing an iterator from a different list. Same thing here. That's very silly. Maybe you even saw me making that mistake and you've been waiting for me to find it. Well, I found it. That was a silly one. Let's not get too comfortable though, because sometimes I can get a little comfortable and I start talking about like how, oh yeah, whenever we fixed everything, right? And then it turns out that we had some more problems. So I'm not falling into that trap this time. Why is it so slow to build a file system? Okay, I don't know what's going on with my machine there. I think it was some thermal throttling. I need to get a better machine at some point, but I have let it cool down now, so seems like maybe I didn't build the whole file system correctly though. So give it another chance. There we go, and we are still screwing up, so good thing I didn't get too cocky. what else did I mess up? Da, 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 da. I guess we can turn on malloc debug, tell us what's going on. Some days I feel like this computer is gonna catch fire. It's also getting louder every day, it seems like. But I wonder if it's something I'm doing, like keep writing more code that he has to compile over and over. I guess that's kind of annoying. We'll see. Okay, so run out of memory and absolutely no debugging. We don't get a backtrace or anything. It's crappy. Malloc, the entry point should. I shouldn't. It doesn't log anything by default. Let's just do this. Server, system server, and sync and run. Oh, we have to make. Oh, not really sure what I did wrong here, but try that one more time. Okay, so you're definitely mallocing a lot. That's cool. I guess we were mallocing a little too much, probably. Did I do something here that incurs malloc? Oh, shit. Of course I did. Oh, dude, I'm such an idiot. I can't use doubly linked list like that. It does a freaking new. And the code, I was even editing that code. It's prepend node does new node. And this node is malloced. So you try to malloc something, it will malloc. You try to malloc, it will just malloc forever. Okay, well that's very silly. But at least we made a little prepend thing. I'll just commit that. Add doubly linked list prepend. Also make it possible to remove with a value type. Iterate. Because why not? Okay. So that sucks. Then what can we do about this? I guess we have to think differently then. We can't use a doubly linked list just like that. And we had the inline linked list, but if we want to traverse the inline linked list, then we will end up screwing ourselves, because that list, all the next and previous pointers are inside this memory that we're not protecting. But what if we put them, we go back to inline linked lists, but we have a separate list for all of the rainy day blocks that we know are protected, and then before we try to do anything with that list, we know that we have to like unprotect it. I think that could work. And that list could even be singly linked, because we only care about, like, it's more like a stack, right? You only care about taking something from the top of it. So we'll put them into an inline linked stack instead, and then I don't know if we'll need a separate class for that. I think that's just something we can do here. And the point of doing that is that otherwise, if we use that inline linked list the way that it is, then when we try to take something from that list, then we will also update the next block, because we take out the first block in the list, then the next block becomes the first block, and his previous pointer has to become null at that point. So we don't want to do that because that would force us to also unprotect that block temporarily. And it would be cool if we could avoid that, right? Because it would be one less unprotect call. So I think we can do this. So had a little bit of a bad start here, but we're learning about our program. So all of this code, basically crap. Or we can actually go backwards to just use the undo feature of QCreator and protect. Once we have the unprotects in place, that's when I started doing this stuff. Okay, so now we're going to add a separate list here, which will not be an inline linked list, but it will be the rainy day block list. So we'll call it like the empty blocks, I guess. Let's say chunked block, empty block queue. Yeah, we'll call it an empty block queue. And let's see, how do we do this? I would like to avoid updating all of them, but maybe that's not super avoidable. The more I think about it, the more it seems like we're going to have to unprotect 2 blocks. I'm sure that there's some clever way to avoid that. I'm just being a little bit dumb right now. Let's just start with this. Let's see what we can come up with. So rainy, where's the rainy? Kept for a rainy day. So here, what we currently do is that we do this thing here where we remove the block. If we're choosing to keep one around for a rainy day, then we move it to the tail of the list for the size class of the usable blocks. But this logic is just gonna go away, and we're just gonna always remove it from the usable blocks list, and instead it's gonna be in the queue, kept for a rainy day. So I guess no. Okay, yeah, this is gonna work. Then we just have to set his next pointer to the current head of the queue, and then protect this guy, and then we should be good. So block, and next is empty block queue, and then allocator, empty block queue, block, boom. So let's call this free but kept. Free but kept. Maybe free kept around. Or what's an even better name for this? Free cached. Yeah, that's kind of nice. Maybe we should do this also so that we can know exactly what kind it is. So we would do something like this. Free. We can say like that. Then you know that it's one of these. And it will still look that. You'll still be able to tell what the chunk block size is. Okay. And then when we reuse one, it's going to be a little more to think about there. So we decide, wait, hold on, usable blocks. So if we don't find a block in the usable block list, now we have to look in a separate list. So we probably want to keep, we want the blocks in the empty block queue to sit there for as long as possible, because the longer they sit there, the longer time we have a chance to catch a use after free by them sitting there, right? So we'll just keep them there for as long as possible and try to use some of the usable partially filled blocks instead. So we don't have a block. That means that we have to look in the 1, 2, 3 empty block queue. Or actually, we don't have to look in that queue. We just have to pop one from the queue. So if there's no block and allocator empty block queue, because we can read the pointer even though it's protected. We can null check it, right? And we don't have a block. There's one in the queue. Then all we have to do now is say by the way, wait, hold on. When we were freeing a block and putting it in the queue. Block next is allocator into block. Yeah, we were doing that right. Okay. Just wanted to check that we put null in the thing that ends up in the end of the list. So okay, so we have something in the queue, and we will empty block queue. Or actually, we can even do block is equal to allocator empty block queue. And then here, now this is a tricky part. So we can't do this because that would require reading from the pointer. So we need to know how big would m size be, but we can probably figure that out anyway. And actually, in the case of a chunk block, I think they're always going to be one page. Or are they? Chunk block is always one page large. Yeah, so we can get away with just using page size instead at the moment. Maybe this wouldn't last forever, but right now it works. So we can just do that same thing here. Maybe in the future we would change this to something else, but right now, this is going to work for us, so we can just hard code it like that. It's fine. Okay. So now we take it from the top of the queue, we make it readable and writable again, and then we want to make sure that we update the allocator empty block queue can now be set to block and next. And then here we just want to reinstate this name. Well, we can call it like reused. This is kind of neat. This will tell us if the optimization is working. Okay. I hope that I figured this out in a nice way now. This type of stuff is really cool, I think. I like this. I like this type of thing. It's fun, and it's kind of sneaky and clever use of system mechanics. And what have we messed up here? We are in remove, something that's going wrong. Okay, well, that's probably my bad. Probably we are being a little bit silly somehow. Call free. We're removing something. Where's remove? I guess we want to put it back. Actually, we need to put this thing back in the usable blocks list after we reuse it. So reused. allocator, usable blocks, prepend, block. We prepend it so that, or wait, we should just do the same thing that a new allocation would do. So here we do append, so let's do append here as well. And we also need to increment the allocator block count, and I was forgetting all this bookkeeping stuff. So I guess we need to, or no, actually, we shouldn't increment the block count, because the block is still owned by the allocator. It's just that it's in the empty block queue rather than in the usable blocks list. So the counter stays the same. Okay, we are booted. And let's look at some system monitor stuff. All right, show me some of those. There's some free right here. It's not writable, it's still readable. We need to do something about that. And down here we can see reused and free. Kind of cool. Let's open up Windows Server, see what he's doing. My computer is very laggy. I see that it's doing a bunch of stuff over here. I don't know what's going on. Maybe spamming that output every time you call mprotect is not the best idea. So let's not do that. Okay, let's look at Windows Server once again. Maybe we'll open a web browser. And, oh, hold on. Come on, Windows Server. Or I want to see a web browser, actually. Okay, it's so, sometimes it's so annoying when they jump around like this. I just want to... Because opening like a different web page should definitely cause a bunch of this stuff to move around. Yeah, okay, so now we got all these free ones, and they're not writable. This is, I mean, this is so cool. I really like this, and it does seem stable, so. We should, let's commit this, and then we can go to work on prot read as well, because right now, we only care about prot write, so we're not protecting against read access. So let's see. Let's do something here like let's see. Mark okay. Completely empty but cached. Empty but, what do we call these? Empty but kept around. Chunked. Let's say protect empty but kept around chunked blocks with prot none. Keep a separate list of, separate queue of empty chunked blocks. Each allocator. These the underlying pages for the underlying memory for each block is mprotected. Prot none to prevent to provoke a crash. Provoke crashes on use after free. This is not going to catch all use after freeze, but if it catches some, that's still pretty nice. Yeah. Yep, okay. So what else? I guess we don't have to say much more about that at the moment. So actually, we can mention something about the names. The mmap, or the memory region names are now malloc memory region names are now updated to reflect the reuse vs what do we call this? Reuse status chunked block xx size free or reused. Yeah. Okay. This is very neat. Very, very neat. Okay, so here, let's say it's set readable, prot and prot read. And then we have to implement set readable because that doesn't exist. So we can just copy this and get it right this time. And we have the readable flag here, but I wonder what that's actually used for. What do we do with it? It doesn't seem very much. I think if a region is readable but not writable, I mean, writable but not readable, I'm not even sure if, can you even do that on x86? Because if we look in the page tables, so what is it called? Page director, page table entry. There's a read-write bit, but it's just a bit. So it's either it's writable or it's not writable. Now you could no, it will say not. Is it possible? Write only memory x86 paging? Does anybody mention write only? Maybe this is not the most commonly wanted thing. Okay, let's not worry about that right now. The important part is that if we have prot none, so it's neither writable or readable, then we can certainly set the page as not even present, which would provoke a page fault in all cases. So let's look at the set writable flag. So normally when we map a region, let's see, is it in remap page? Wait, what's the difference between map and remap? I don't remember. I think maybe we just have to fix both of them. So when we map a region, then oh, and remap page is mapping an individual page in the region. Okay. So map maps the whole thing. Then we set the writable flag of the page table entry here. And if it's a cow page, so it should copy on write, then we make it not writable, and that provokes a page fault. But yeah, right, so here's the is readable flag. So I think we should do, if is readable is false, then we should probably just set the page as not present. Basically what this fix me here is talking about. So we'll do that. And I guess the same thing up here, remap page, we'll just set it to is writable. That makes sense. Should cow. Should cow is a little bit suspicious. Here, because this I'm not trusting this right here, because like if you get, say that you get a page fault, right? And you get a write access page fault that says like, hey, you can't write to this piece of memory, but it's copy on write memory that we got from a fork parent. And then we just handled cow fault, where we copy the parent's page and then make it writable in the child. But what if it is not only a cow page, but also write is not set? I think we should not allow you to access it then. I think. Protection violation. So here, let's say is writable and should cow. Okay. Otherwise, we'll just fall over this. I think that's a sane change. But actually, let me do that one separately. So, cow, don't cow if not is writable. Frick fix me. And we'll fix that in a moment. And I'll even copy this here. Okay, just so we don't forget. So let's test this out. Wait, it shouldn't be is writable, it should be is readable. And yeah. Now I'm doing a full rebuild, even though I only changed the kernel. I didn't have to do that. Sometimes I forget. I would so like it if, like the more bugs I can find in the system, the better, right? And it's so nice to add little things like this here and there all the time and keep adding more and more of these sanity checks, because the moment these things catch a bug, it makes it all worth it. And even if it doesn't, it's still so much fun to make these mechanisms that I don't even mind. So browser, and hit me with the browser, bro. Okay, and stop jumping around so much. Okay. Tap, tap, tap. Look at that guy. He doesn't have an R-bit either. I guess we should try to write a crash test for this. So we'll make a crash program. We'll say write to freed memory. Write to freed but kept around. Freed memory cached by malloc. Still cached by malloc. And we'll have read from freed memory still cached by malloc. And I don't even know what the argument for these is going to be called. I guess, I don't know, x, we'll call them x and y. X will be write, and y will be read. It should be the other way around. Oops, 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 oops. Oh. Maybe dash y. Yeah. Okay, so x is read and y is write. How do we crash now? So I guess what we want to do is we want to allocate something and then just free it. And then, yeah. We'll do pointer is a U8 malloc, some cool number, like, I don't know, something big that's going to give us our own special little chunk block in malloc. And then we'll just say free putter. And then we'll do volatile foo is putter. And void foo. And assert not reached, because we should have crashed for that. And we'll do one for writing as well, so it will be the same basic concept, except we will write to that pointer. So putter is x, and we shouldn't reach here. Write from freed. Yeah, I didn't do that right. Okay. Crash x. Asserts that didn't work out, and y also did not work out. Why don't they work out? I wonder. So do we get dumps when we do that? Okay, so let's, we're gonna need some region dumps from these guys. How do we provoke some region dumps? Can we do crash? Let's also print out the pointer that we're using. So debug putter is, or let's debug print. Putter is p. Because I want to see what it is before we write to it. Okay, so crash-x, we use this pointer here, 142D. 142D is a big allocation block. Ooh, shit. Okay, I made it too big. I'm going to need to do something slightly smaller. Otherwise, we're not hitting the chunked allocator. We should probably do this for the big allocator as well, but that one is a bit different. So maybe we don't do that right now. We'll just use a smaller 1 kilobyte allocation to give ourselves a, make sure that we get a chunk block, basically. Crash X, and what happened to us? Wait, what actually happened to us? Hang? What does that make us hang? Okay, what about crash Y? I am confused. It's going to be something silly, isn't it? Crash, stacks, what are you doing? You're in main, okay. The frick? Crash, putter is this. Is crash doing something silly? Does an undefined opcode? Does crash not work? Definitely breaks. do we get into some kind of a loop somehow in the kernel? Maybe we get a page fault because it's not readable, and then we try to fix that and it just breaks and does it over and over and over. Let's see if I can turn on page fault debugging. This is very noisy. Crash X. Yeah. Okay, so it's just getting in a page fault loop. So we'll go in handle page fault right here. Okay. So it's a page not present fault, but it's not going to be in kernel memory. It's going to be in user space memory. So we're down here. We get a fault in a region. So we tell the region handle is fault. Okay. And it's a page not present fault. The underlying VM object is not an inode. So we assume it's a 0 fault. Is that handle page fault? I guess we're probably thinking that it's a 0 fault. Let's see what this code says about it. I feel like it's going to say that. Yeah. Crash X, and it's 0 fault. Okay, so this is not a 0 fault. We're handling this wrong. Because we are getting a page not present and the page is not readable. So if is readable, it's false. This means that we have committed a boo-boo, if you will. So we will instead say debug printf np non-readable. Yeah. Fault in region P, page number U. Okay, and then here we can say this page indexing region. Okay, and we will return page fault response should crash. Crash X. We get a non-readable right here. Very cool. And crash Y. Seg violation. I try to write to it, and it's just the same. Yeah, we get a write to this address, and it also doesn't work. Cool. So it works. That wasn't that tricky. Just had to fix up that thing in the page fault handling. So what's the whole thing? That's the crash test. It does a whole bunch of unrelated fix-ups. It's kind of sad. Ugh, it's so ugly. Can we just not do them right now, please? It's gonna mess up my beautiful diff. Ah. Oh. That one looks a bit silly as well. I want to be correct, but I don't want to mess up my beautiful diff. So, okay, and then we don't need these crashes. I mean, we should get rid of these crashes actually, because otherwise we don't know that we're testing the right thing. So let's make sure that we are still doing the right thing here. Crash X, crash Y. Yeah, we're not getting the assertions, we're getting the proper crash. Very, very awesome. And yeah. This is definitely good enough. So yeah, we're using the isReadable to mark whether a page is present or not. Yep. Okay, so commit kernel. Oh, hold on. Git add kernel. Kernel. Crash on memory access in non-readable regions. This patch makes it possible to protect the memory with prot, prot read, to make mmapped make memory regions non-readable. This is enforced using the present bit in the page tables, a process that hits an NP page fault in a not present page fault in a non-readable region will be crashed. Cool. I realize now that I should have just included this into the patch. So we'll put the crash program in there as well. And now I realize that I should also write the little man page about it. Just add the options. X read from recently freed memory. Opportunistic malloc guard. Tests. Something like that we can say. Okay. I mean, we could have also here, we could have just done, we could have done mmap here manually, but this seemed a little bit more fun. So it's all the same. Oh, frick, I forgot to commit that. So amend and sync and run. Let's look at the man page in the system so that we see that it looks good. Help. Crash. Oh, frick, where are all the options? That did not look good. How did they mess this up so much? I mean, this should be like this. Wait. This doesn't look right at all. All right. Oh, it seems like this is broken. Oopsie. Maybe I broke this in lib.html. Well, there's something for me to frickin' fix me. Options. Lists in help are broken. Did I break lib.html? Oopsie. Fix it. Okay. I guess we can still test this using the man command, so we'll use the man crash. Oh shit, they don't even show up here either. Well, then it's probably not my fault. It's probably lib markdown is broken. Crash. Whatever. Okay, so this separate issue. We'll worry about that at some other point, not right now, because I don't want to get too sidetracked, because I also had this guy right here, don't cow if it's not writable. So region CPP is right here, if is not writable, and should cow, right? No, wait, hold on. If fault access, so it has to be writable. We don't cow anything non-writable. Yeah. I'm not sure what should happen. Like if you have a writable but not readable region and you get here because you get the page not present because it's marked not present because of the readable bit, then we'll say that it's a non-readable fault, but you try to write to it. So it's unfortunate, but I'm not sure how to implement that. Maybe somebody knows how to do write-only memory on x86. I'm not even sure if we need that, but if it's possible, it would be nice to do it. Okay, so kernel don't cow pages that are don't cow non-writable pages. If we get a page fault, a cow page marked a cow should not be cowed, should not trigger a cow if the page is non-writable. I think this makes sense. Okay, and probably we're going to be good here for today. So X and Y, and we got a little system monitor. We can look at the terminal, memory map. Well, it's not as exciting as one of these more active programs where you can see state actually is not changing wildly. Where am I supposed to look if I want to see wild state changes? Maybe nowhere. Maybe that's okay. Go into the browser. And lately I start feeling like it's fun just to use the system. It's starting to, like, coming into some kind of thing now where it's starting to be fun to explore. I find that the more metrics and things and like, just like for instance, yesterday when I added these, this data here that shows you how much input-output traffic in different categories you can have per thread, it just makes the system so interesting to mess around with. And it sort of opens up this thinking about, well, how could we make this better or worse if you wanted to. I don't want to make it worse, but just trying to see this thing move and shake a little bit. Where are all the? Okay, I don't know what I'm expecting to happen. A lot of big allocation blocks actually. I guess this is the PNG images that we're downloading. Maybe those shouldn't be malloc memory. Maybe they should be mmap instead. These are pretty chunky allocations. I mean, actually, what we should do is we should download these things and put them in some sort of cache, bitmap cache, or I'm not sure exactly, but I remember this. This was some paging bug that I had that would cause some windows to get this glitched out stuff sometimes. I think it was that you had like this overlaying parts of memory, so like two pointers would actually point to the same physical memory even though they didn't know it. So like there was data being written into what we thought was malloc memory, but was actually the backing store for this window. Good old times. Anyway, I'm very happy with this thing. So cool. Okay, so I mean, just look at all of these not readable, not writable areas. These are all memory access failures waiting to happen, which is great. Okay, I'm going to stop fawning over this now and just say this is going to be the end of the video. So if you made it this far, then I thank you for watching and for hanging out with me while we work on this today, whatever this was. And I hope you saw something interesting. Maybe I said that already. And check me out on Patreon and GitHub sponsors if you're interested in supporting my work. Otherwise, don't do it. That's fine too. I'm just happy to have company while I hack, because I'm going to hack no matter what. So thanks for checking this out, and have a great day, and I will see you next time. Bye.